This is Chapter 15, and welcome to Section 15.1, an Introduction to NMR Spectroscopy. In this chapter, you're going to learn about one of the most powerful analytical and structural determination tools that we have in organic chemistry, which is NMR spectroscopy. NMR spectroscopy is pretty neat because you can use the simple number of protons and or neutrons in the nucleus to find out exactly where the atoms are connected in a molecule and what those atoms are connected to. So the typical or the most common nuclei that are studied in this are the proton, H with a proton, a hydrogen with only a proton, that is, and no neutron, carbon-13, the isotope nitrogen-15, the isotope fluorine-19, and the isotope phosphorus-31. Each of these has an odd number of protons and or neutrons. So NMRs basically work on this on the principle of magnetic force lines, in that you have a proton that's spinning, in that each subatomic particle has a spin, okay, just like an electron does. It's weird to think about them as having a spin, but let's say for our purposes that they do. So consider that one is spinning clockwise and one is spinning counterclockwise, or perhaps one is spinning up and one is spinning down. It doesn't really matter. The point is that you have all of these in different spins, and they could be in different orientations and locations in the molecule, but upon applying them on a magnetic field, they all align with the field. So if you notice in figure 15.2b, the applied magnetic field is vertical. So each of the spins where they were randomly distributed are now either going down or going up. And so we at least have them all in the same orientation now. But what we want to do is to be able to find out which are in the one spin state and which are in the other, up and down. And that's what we're going to do with NMR. So whenever a nucleus with a spin state of alpha is radiated with enough energy to promote it to the beta phase, then it will do that. So then you have a flip in the spin state, and you could perhaps measure the amount of energy that it takes to do that. And in NMR spectroscopy, we're going to do just that. We're going to put a tube or a molecule in the middle of an induced magnetic, or in the middle of an external magnetic field. There will be an induced magnetic field that follows, and will follow how much energy that it takes to flip the spins of any one proton or other NMR active nuclei. The effect, or this effect of being able to flip the spins, is called diamagnetism. It was discussed in the opening of this chapter. It essentially means that if you didn't have diamagnetism, all protons would absorb the same frequency of radio frequency radiation, and this wouldn't work. Well, we'll get into why radio frequency radiation is important in the next chapter, but let's just say that we're going to use NMR spectroscopy to find what types of protons are present or in a molecule, or what types of hydrogens are present in a molecule, by irradiating them with radio frequencies, and then using how much each is shielded to find the structural characteristics of those molecules. So that's it for section 15.1.